All right, so we are back for part two of our confidence intervals lecture. And as I mentioned before, having spent a great deal of time laying the theoretical groundwork for how this is going to work, I want to show you how this actually works in a particular canned example. So at the very end of the last bit, I told you about standard error, which is the population standard deviation divided by the square root of n. Or at least that's what it's equal to. The standard error itself is actually the standard deviation of the sampling distribution. So again, sampling distribution is the distribution formed by the means of samples taken from the same population. Okay, so what I want to do is take a look at how the shape of the sampling distribution compares to that of the population distribution by first plotting a normally distributed density curve in R. And I'm going to just crank out some R commands here, and you're welcome to follow along if you'd like at home. But yeah, this is using our sort of plot function for normal distributions again, and this particular one has a mean of 5 and a standard deviation of 2. And we're going to plot it from 0 to 10. We've actually done this before, so hopefully it looks familiar. But yay, there's a normal distribution. And I'm going to say this represents our population distribution. Yeah, so if we consistently took the samples of 100 items from that underlying distribution, we'd expect the mean of the sampling distribution to remain the same. This is part of the central limit theorem. The mean of the sampling distribution is the same as the mean of the population distribution. But the standard deviation, which we're now calling the standard error, is going to be that underlying population standard deviation, sigma, divided by the square root of n. So that underlying population standard deviation is 2. N is 100. We're taking samples of 100 items from the population each time. Square root of 100 is 10, so 2 divided by 10 is 0.2. Like I said, this is a canned example, and I'm trying to keep it relatively simple so that we can kind of just see how this all works. Okay, so that's a lot narrower standard deviation than what we've seen before. It's 1/10 of what we saw before. So let's plot that. And I'm going to plot this on the same graph as I just showed you. The way I'm going to do that is with an add equals t. And I'm going to make this one red over here. And the only thing else that's going to change is that the standard deviation is 1/10 of what it was originally. The mean winds up being the same. And I plot that. And what happens, you didn't see that right away. Apologies. But we get a graph that looks like this, which is kind of funny. So the red one is the one I just produced. This black one is the population distribution. So this one has a much broader standard deviation. So it's fatter overall. This one is super skinny, and basically the entire distribution is squeezed in this little middle section right here. So much so that the top of it goes way up above that because the whole thing has to add up to 100%. We don't need to worry about that so much, but this doesn't really help us understand what's going on. So I'm gonna plot it in a different way. By plotting the distributions in the reverse order. I'm going to show you the result here on the slide because it's inevitable if I want to switch over to R. So I'm going to just show you these are the commands I'm going to use here. I'm just going to do them in the opposite order. And then it'll wind up looking like this. And I'll just kind of verify that by actually putting these commands into R. Whoop. All right, so if I go back plotting the sampling distribution first, I get this. I see where the top goes. And then if I plot the population distribution after it, and here I'm just, changing the standard deviation and then adding it to what I plotted before, then I see the whole picture basically. Here's my sort of smudgy fat population distribution down here at the bottom, and here's the sampling distribution poking up at the top. The point is, we already know because I just put these parameters into the system, but the standard deviation of the sampling distribution is much smaller than the standard deviation of the population distribution. So it's going to squeeze the whole thing into the middle a lot. And that's kind of the difference between standard error and standard deviation in a sense, because the standard error is something that applies to the sampling distribution, this sort of meta construct of means that we're creating from the population. And what winds up happening is that the whole distribution narrows in or zeroes in to basically a smaller range of values. Okay, so that is just showing you differences in standard deviations for a normal distribution. What relevance does this have to what we want to do? So if we have a mean of a sample from whatever data we've collected, it will fall somewhere on our distribution of sampling means. So again, just to review, let's say we're looking at a population like, say, all speakers of Canadian English or something like that. We don't study all speakers of Canadian English. We take a sample of them, like maybe 20 from our intro linguistics classes, and then we calculate some basic data from that sample, like what is the mean F0 of those speakers of Canadian English that we actually looked at. So what we have is that sample mean. I'll show you an example exactly of F0 in a second, but let's say, we have a sample mean of like F0 equals 200 hertz or something. How can we know from those 20 speakers of Canadian English what the population mean is? What does that tell us about the average F0 for every speaker of Canadian English in the world? Well, we won't know exactly. Like I said before, the sample mean will not necessarily equal the population mean. And in fact, in most cases, it's not going to equal the population mean. In some cases, won't be even close. So for that reason, what we have to do is guess. Basically, the sample gives us some information about the population that enables us to make an educated guess, which is better than a completely uneducated guess. But it's not going to be perfect. So because it's not perfect, what we guess is that the population mean will fall within a certain range of values around the sample mean. And this is where the concept of a confidence interval comes into play. That range of guesses is called a confidence interval. So instead of saying, well, I got, a mean of 200 hertz of F0 from my sample of Canadian English speaker, therefore the population mean is 200 hertz. You're just going to kind of use that as a benchmark and say, well, it's going to be like in a range around 200 hertz, like maybe 180 to 220, something like that. Except you're not going to be as loosey-goosey about it as that. There's, like I said, there's a series of principles you use and apply to a situation to give you an exact interval, which is going to be your official guess about where that population mean is. Okay, so how does this work? Number one, it can work in different ways depending on how accurate you want to be. So my second question is, how big do you think the confidence interval should be? That's something you can tweak depending on how sort of confident you want to be about your proclamations of, what population parameters are. So another way to ask this question is, how often do you want to be right and how often are you willing to be wrong? I'll give you a second to think about that. I think some people are probably more willing to take risks than others. When I ask this question in class, unfortunately, I want people to kind of like tap into sort of like their primordial instincts about this question. And what I usually get is not primordial instincts. It's convention, because there's a conventional way to answer this question, which is to say, we're going to try to be right 95% of the time. And so this is a long tradition, goes back like about a century or more in the world of statistics, to say, well, this translates to being right 19 out of 20 times, and that 1 out of 20 times is just, oh, whoops, sorry, I'm not perfect either. So you can think about this like, this would be good enough for an A grade in a class, right? Like a mark of 95%, but it's not 100%. We are not going to be able to be 100% correct in stats ever. It's just too much work to do that. And in fact, you wouldn't even need stats if you did that. Like if you went out and measured every sort of speaker of Canadian English or everybody in your population, then stats would no longer apply. It'd just be like a lot of grunt work. We're not going to do that grunt work. We're going to do the stats work instead to help us out, to be a little more efficient. And the way we do this is by thinking of our data in terms of how they sort of fit on a normal distribution. So what we want to do is translate being right 95% of the time into a range of values on a normal distribution. So we're going to start with the sample mean, which falls somewhere on a sampling distribution. And then we want to specify a range that encompasses 95% of that sampling distribution. So just to review again, I said we're going to get like, a statistic from our sample, like the mean, and that will almost certainly not be equal to the population mean, that parameter value. but it will fall somewhere on our sampling distribution. Remember, when we plot a sampling distribution, it's just the distribution of sample means. So the mean fits on there somewhere. We only get that one picture of the sampling distribution, though, but we can guess about how that sampling distribution looks. And based on that guess, we're going to grab 95% of that distribution in total. So remember, the mean of the sampling distribution will become closer and closer to the mean of the population distribution as n, the number of items in the sample, becomes larger. So if n is suitably large, then by grabbing 95% of the sampling distribution, we will grab a range of values that will include the population mean 95% of the time. Because that sampling distribution mean is supposed to be equal to the population mean as n increases in size. The other thing that we get out of n increasing in size is that the sampling distribution itself becomes more normal. It falls into a normal pattern, a normal distribution. Because we're dealing with a normal distribution, we can think about things in terms of z-scores for the sampling distribution as well. And that's going to kind of ultimately be the trick we're going to use to make this magic happen. Okay, so how do we grab that 95% of the sampling distribution? So we start by putting our sample mean right in the middle of our slice. And it's as good as any other point on the distribution, more or less. We don't know that it's in the middle of the actual sampling distribution, but like I said, we're guessing to a certain extent. And I'll reiterate this point again, we can almost certainly be sure that it's not actually in the middle of the sampling distribution, or it's not actually the mean of the population distribution. The odds are against it being that exactly correct, but in general, it should be in the neighborhood. And like I said as well, because we know we're in the neighborhood, we have to figure out how big the neighborhood of our guess is going to be, how big that interval is that we're going to make our guess for where the population mean happens to be. So we're putting our sample mean right in the middle of whatever slice we're taking from the sampling distribution, and then we're going to add and subtract 1.96 times the standard error to it. Maybe that number rings a bell, maybe it doesn't, but the reason that we're doing that has to do with this 68%, 95%, 99.7% rule. So like I said, we're going to try to be right 95% of the time when we do this. And you might recall that 95% of a normal distribution falls within approximately 2 standard deviations of the mean. More specifically, it falls within 1.96 standard deviations from the mean. So to do this, we have to use the standard error, or a guess at what the standard error is. In other words, what that standard deviation of the sampling distribution is. Because we're going to use that to basically calculate how much of a proportion of the sampling distribution we're grabbing. Okay, so we're estimating the 95% proportion around the population mean by adding or subtracting 1.96 times the standard error to it. What we get out of this is that 0.975 of a normal distribution falls to the left of the point. 1.96 standard deviations greater than the mean of the distribution. This is a review, but just in case you'd forgotten. And then we also have 0.025 of the normal distribution falling to the left of a 1.96 standard deviations less than the mean of the distribution. You can go back and look at the z-score lecture if you've forgotten all this. But what you wind up getting out of this is 2 points at z-scores basically at 97.5% of the distribution and a 2.5% of the distribution. In between those, you get 95% of the normal distribution. This is, again, just this 68, 95%, 99.7% rule, but the crucial number to remember here is this sort of z-score of 1.96. And if you multiply that by the standard error, you find out where these sort of values are on either side of the mean. And those limits are going to form the confidence interval once you get to that point. Okay, what you wind up with in the end is confidence interval equal to this value. It's going to be x bar, which is the sample mean, plus about 1.96 times the sample standard deviation, s, divided by the square root of n, or the number of items in your sample. This is sort of just the, if you actually have to do it, equation for calculating a confidence interval, but try not to forget all that underlying theory that I talked to you about up until this point. That's where this is coming from, basically. Also, this 1.96 times s divided by square root of n part of this equation is known as the margin of error, which is a term you might have heard of somewhere down the line. And in fact, it's the title of the slide as well. But basically, it's that range that gets specified around the sample mean itself when you're calculating a confidence interval. That margin of error will grab you 95% of the estimated sampling distribution around the particular sample mean that we got from our data. So we're guessing a range. We're saying we think the population mean is within this range of values based on what we learned from our sample. But an important point to remember here is that we may be right, but we might also be wrong. The actual population mean might not actually be in that range of values. And unfortunately, there's no real way of knowing whether we got our guess right or not. We just know based on the mathematical theory that we're grabbing about 95% of the sampling distribution. So 95% of the time the guess should be right, and then the other 5% of the time it's not going to be right. And what I mean by the guess being right is that the population mean will be in that interval, and then the other 5% of the time it won't be. Like I said, we're committing to being right 95% of the time. The work is too hard to be right 100% of the time, so we're going to have to sort of just sacrifice and make a few errors along the way because we know that we're guessing. We're making educated guesses when we do this. As linguists, maybe this is a little bit awkward because we're used to having that sort of click feeling when we see the pattern and everything sort of just fits into place, and that's nice. We're not going to get that with stats, unfortunately. We're going to get guesses and sort of a little bit of risk-taking that goes along with it. So we might be right, we might be wrong, but at the very least, I want you to understand how that process works. So theoretically, what we wind up with this is the population will be within our confidence interval 95% of the time if we use this sort of multiplier, this z-score multiplier for our margin of error. Okay, so what does this look like? I want to show you how this would work with the example distributions that I plotted in the previous video. Both of these were normally distributed with a mean of 5, and the sampling distribution itself looked a lot taller than the population distribution because its standard deviation was much smaller, or the whole thing was narrower, basically. Okay, so there's my population distribution, there's my sampling distribution in red. And so let's say we take a sample of 100 items from the population, which would give us this sort of sampling distribution. And then what we wind up with for this particular sample is a mean of 5.2. The means of both of these distributions, the underlying population and also the sampling distribution we get from it, should be 5, because if n is big enough, then the sampling distribution mean should be equal to the population distribution mean. But like I said, we're not always going to get a mean right on the population mean from our sample. We're going to get it somewhere on this sampling distribution, but, not always right in the middle. So let's guess that it's at 5.2, or just, we're creating an example here. It's going to be 5.2. Okay, here's the tricky part to remember. This is our data. This black asterisk is the data we got from our study. In theory, it's coming from this sort of picture that underlies the whole process, but this is like the phonetics-phonology split, right? We don't see the phonology directly. We don't see these underlying parameters directly. We just see the observation that comes to us on the surface. So what we get is just this asterisk, and we're trying to draw some sort of inference about the population on the basis of just this, basically. So we only get 1 point on the sampling distribution itself. We don't see the sampling distribution. And then the other thing we get, though, in addition to the sample mean, is the standard deviation of the sample as well. So we know a little bit about how much variation there is within the sample itself, and from that we can make a guess about how much variation there might be in the overall population. But that's an assumption. So we assume that the sample standard deviation is the same as the standard deviation of the population. Again, that's not necessarily the case. It's kind of more likely to be the case if n gets bigger and bigger, but it's never going to be exactly the same, just as the sample mean will not always be exactly the same as the population mean. We're making guesses kind of all the way down the line here, but we do it to get sort of a relatively powerful tool at our disposal. So we can't, don't just take this for granted. It's not a trivial assumption that these two standard deviations are going to be the same, but we have to start somewhere if we want to figure out what's going on underlying our data in the population. Okay, so like I said, we're going to guess that the sample mean is the population mean, which means that it will also be the sampling distribution mean. And we're also going to guess that the sample standard deviation is the population standard deviation. And, at this point, you might be thinking, well, I took one sample and I'm just assuming that the sample mean is the same as the population mean, even though I know that's probably not the case. And I'm also saying, well, the sample standard deviation is population standard deviation, even though I know that might not be the case either. Like, why am I even bothering with this other stuff? I can just hey, we're done, because I got a sample of data. This process helps you create sort of a more responsible and realistic picture of how accurate these assumptions are, I guess you could say. So we're not going to just keep this one number and say that's it. We're going to create a range of intervals around that number and say this reflects the population parameters like a certain percentage of the time. We're acknowledging that these guesses are not going to be perfect and we can't just stop there, basically. But based on these assumptions, we have to start somewhere. We can create an estimated sampling distribution. So like I said, according to the central limit theorem, the sampling distribution mean should be the same as the population mean. So we're just going to guess that it's at our sample mean value at 5.2. And then we're going to grab 95% of that distribution by creating an interval value of values in which the population mean will fall 95% of the time. Okay, so I'm going to zoom in a little bit here on our distribution to show you how this is working at a more fine-grained level. So like I said, here's our sample mean, and I tried to plot it at about 5.2. My artwork is never going to be totally exact either, so kind of bear with me here. But this is our sampling distribution mean, or actually our assumed sampling distribution mean in orange, which we're just guessing represents the underlying population. But we don't know for sure, right? We never know exactly what's going on underneath the surface in stats. We do know, though, that we took 100 items in our sample, so that's a given, that's an observable. We know on the basis of the data we collected from that sample that our sample mean is 5.2. The sample standard deviation is 2, and just for convenience's sake, I made that exactly the same as the population standard deviation, just to keep this whole example simple, but it could be something different like 2.5 or 1.3 or whatever, right? But let's say it's 2, and then we can estimate our standard error to be the sample standard deviation divided by the square root of n. And we've kind of seen this math before when we were plotting the initial sampling distribution standard error. It's going to wind up in the same place and just be 0.2. Just keep in mind that it could be a little bit different. And then in fact, if n were to change, like if n got bigger, this number would go smaller. And then if n were smaller, then this number would be bigger, so on and so forth. But right now, we'll just say our standard error is 0.2. That's our guess for what's going on here. And now we want to create a 95% confidence interval. And to do that, we just use that equation I showed you before. So we're taking the sample mean of 5.2. And then we're either adding or subtracting 1.96 times that standard error to it. So 0.2 times 1.96, you can add that to get sort of the higher end of the confidence interval range. And if you subtract that, you get the lower end of the confidence interval range. This product, 1.96 times 0.2, winds up being 0.392. If you do the arithmetic there. And then if you add or subtract that to 5.2, you get this range from about 4.8 to about 5.6. And that would look like that in this graph. And I'm going to plot out arrows to either side here and say, well, this is my 95% confidence interval. It's this range of values from about 4.8 to 5.6. So I'm saying this is my guess about where the population mean is likely to be. And if I do it this way with these parameters in the process, I'm going to be right 95% of the time. 5% of the time I won't be right. And in fact, in this particular sample, for this particular instance, I might not be right. There might be, the population mean might be 4 or 6 or something like that. But most of the time I will be right, enough times right that I will get an A in my stats class of reality, sort of, so to speak. I'm going to get a 95% mark for this. In this particular case, since this is a canned example and I wanted things to work out, this red distribution is the actual sampling distribution because we know the underlying population mean is 5. And we know what the underlying sort of standard deviations are supposed to be. And like I said, I'm trying to make this simple so it all makes more or less sense to you all. So we can see that the actual mean here is within this range, the orange estimated confidence interval for this particular sample. And so, yay, we're right in that sense. But this is kind of what's going on underlyingly. I'm also going to plot the population distribution here, but this you can hardly even tell is a normal curve because it's spread out so much. So when we only look at a little slice, it seems to be hardly moving or changing at all. Sort of like the flat Earth theory, where something that's massively spherical, like our planet, when we look at it on a very small scale, seems to be flat, but it's not. Don't be confused. Don't let the internet lead you astray. But anyways, the point is we are in this fortunate example getting the population mean within our confidence interval. So yay, we can be confident about that confidence interval. But in reality, you are not going to know. You are just going to get this star, and based on the standard deviation of your sample, you're going to get a range of values around it, but you will not know anything about this red curve or this black curve underneath it because it's just too much work to find out exactly what's going on there. So in this case, our interval does include the population mean. And I'm going to stop there for now and give you a few examples to play around with in the next part of this video. But for now, I think I'll call it a night because it's pretty dark. And I want you to be able to see things a little bit better when I try again in the morning. So I'll see you guys then.